Ryan, man, so good to hear from you. It's funny when I saw your name on the email, your face popped right into my head. I could see where you sat down there in the library in 117, and I think if I remember correctly, there was always a woman you sat next to in class, and you two were kind of like study partners. But I could be getting that part wrong. But I can totally picture your face in my mind. So totally awesome to hear from you, and what a great question to ask about the Monty Hall problem. So I'm gonna make a quick little video here. I actually do this problem in my Math 105 class. I guess we didn't do it in 243, or you would have remembered it, I would bet. But I do it in Math 105, which I never had you in, I guess. So here's the deal. You got 3 doors. I've actually built a model of it because I like it so much. And you hide a prize behind one of them. So you knew that already. So you come back in the doors and you hide the prize somewhere. And then you correctly said in your email that you guess one of the doors, and you only have a 1 in 3 chance of getting it right, which is 100% correct, because the prize is either here or here or here. And assuming that it's a random assignment of the prize, that you have a 1 in 3 chance of getting it right. Okay, the part that gets tricky is the opening of the door throws everybody for a loop. So let's not think about it that way. Let's think about it a slightly different way. Let's suppose that you pick door number 1, and instead of opening another door, Monty goes, okay, you pick door number 1. You can keep door number 1, or I'll give you both doors 2 and 3. Would you switch then? No doors being open. He says, pick a door. You pick door number 1. And then he says, okay, you can keep door number 1, or you can get both doors 2 and 3. Now, hopefully, without thinking too hard about this, that's a no-brainer. Because the prize is only going to be here 1/3 of the time. The prize is going to be here 2/3 of the time. Hopefully that makes sense. So you should switch, right? You should take both doors. And this would be whatever door you picked originally. So let's suppose you pick door number 2. And Monty goes, okay, you can pick door number 2, or you can get both doors 1 and 3. Again, no brainer. There's no guarantee you're going to get the prize, but if he's giving you twice as many doors, it makes sense to take that deal. Okay. So without opening doors, I think it makes sense. You pick a door, he offers you 2, you take 2, because you're twice as likely to get it then. Now let's see how this plays into opening the door. Let's go back to the you pick door number 1 case. Okay, so you pick door number 1, and Monty, this is the original problem now. You pick door number 1, and sorry, by the way, there's a fan blowing directly above my head. I hope I'm loud enough that you can hear me over that fan. You pick door number 1, and Monty goes, okay, you can keep door number 1, or you can switch to door number 2, because door number 3 has nothing behind it. Now, in your email, you said that it feels like since there's only 2 doors left, there's a 50-50 shot that it's here and here, because there's 2 doors left. But you got to remember something. Before he opened this door, you correctly knew that there was only a 1/3 chance that the prize is here. That means that there's a 2/3 chance the prize is either here or here. That doesn't change when he opens this door. These 2 chances have to add together to make 2/3. When he opens a door, he's effectively giving you that door. He's giving you information. The prize is not here. There's a 0% chance that the prize is here. But there's a 2/3 chance that the prize is somewhere between these 2 doors. Well, if there's no chance it's here, that means there's a 2/3 of a chance that it's here. Effectively, it's the same as just saying you get both of these doors. It's just that he's showing you there's nothing here. You still kind of get that because there's nothing there. So you get 2. It's just a cool trick. It's a mind game. Before he opened the door, you knew you probably didn't guess the right prize. But when he opens the door, it throws your mind into a tizzy because now there's 2 doors and your brain wants to make it 50-50. And I assure you it's not. It's still 1/3 here, which means it's 2/3 here. So if you pick door number 1 and he goes, it's not behind 3. Do you want to switch to 2? You should switch, because there's about a 2/3 chance it's going to be behind the door you didn't pick. Now, that's not very satisfying. So what I'm going to do is I'm going to show you what I do in class with my students is I actually have each one of them. I bring a big thing of Blow Pops or Tootsie Pops or whatever they vote on to class, and then I have each student play, and we collect what happens if they stay with their original choice or they switch. You and I can't do that. So what I'm going to do is I'm going to show you the simulator that I built to do exactly that, and hopefully this will drive the point home. Let's go take a look at that now.
Okay, Bryce, so what I've got here is I've got a Monte Carlo spreadsheet set up that basically just keeps track of lots of trials of the experiment that I just showed you one iteration of. It's not as much fun as doing it in class with a bunch of kids, because it's always fun to get kids' opinions on what they think they should do, what might happen in the future. But it's a quick way of getting a lot of data and seeing results quickly. So basically, here's a breakdown of it. Up here, this just keeps track of trials. We've just run one trial when I open the spreadsheet. This guy right here is a randomizer that puts the prize behind a door. Now I'm using quotes in the air, which you can't see because there's no door and there's no prize. This is a spreadsheet. So it's just picking a random number between 1 and 3 and saying that's the goal. You want to get the prize behind door number 2. Now, this one is also a random number. This is where the door you choose. So you chose door number 3. Monty is going to show you a door that doesn't have a prize behind it. Now, this is where it gets interesting and the math gets fun. You can look at that formula up there. It's a total bear. And that's because if you pick the wrong door, Monty's job is easy. So for example, in the video I just showed you, I made you pick door number 1, and I had hidden that lollipop in door number 2. That means Monty has to show you door number 3. So like an example right here, the prize is behind 2, you pick 3. Monty has to open 1. He can't open 2 because that's where the prize is, and he can't open 3 because that's what you picked. So as long as you pick the wrong door, his choice is easy. He has to show you whatever's left. If you pick the correct door, he has to decide between the 2 other doors, and that became a fun little math problem involving the golden ratio, actually, which was totally badass. I did it years ago. Anyway, the spreadsheet does it automatically for you. Whether or not you switch is based on a random number. I made it a coin flip, so half the time you switch and half the time you don't. And the result is, well, there's two ways you can win, right? If you pick the wrong door and then switch to the other door, you're going to win. And if you pick the right door and stay with that door, you're going to win. So right now, in this particular iteration, we're going to move over to this little chart. This is a chart that's keeping track of the results. So in this iteration, you won because you switched, and that's because you had originally picked the wrong door. Now let's play again. That was a stayed and won. If we look back over here, you can see the prize was behind door number 1, and you picked door number 1, and you didn't switch. That means you stay. Let's go back over here. You stayed. Okay, and we can play again. There's a switched and won. Here's a switched and won. Here's a stayed and lost. There's a stayed and lost. I don't know what the hell that little menu was. So what you see is it's just keeping track of lots and lots and lots of. So I'm gonna hold this button down and chitter chatter while we're letting it run. So what you're seeing is you're seeing lots and lots and lots of iterations of this experiment. Now, it might not be inherently easy to see at this point, but there are 2 boxes at this chart that are larger than the other 2 boxes. Hopefully you're seeing it. Switched and won and stayed and lost are both quite a bit larger than stayed and won and switched and lost. As a matter of fact, let me stop it right around 400 here. Let's stop it at 400, right about there. So if you look at these right now, switched and won is right about at 400, and so is stayed and lost. Stayed and won is at roughly 200, and so is switched and lost. And if we continue this, and let it continue to do its thing over and over and over again, that kind of ratio is still maintaining. Right? It's still maintaining. Let's stop around 600. And we'll stop here about 600 and see what happens there. That's roughly both about 600. Well, I shouldn't say they're both about 600. Switched and won is about 600, as well as stayed and lost is about 600. And stayed and won and switched and lost are about half of that, or 309. Let's go a little bit further. Now, hopefully, what you're not seeing, well, let's not get too far ahead of ourselves here. We'll just stop it up at, what's a good number to stop at? We'll stop at like 800, I guess. Maybe 1,000? Nah, 800. I think I'll get the point across. I think you're seeing what's going on. So if we stop these puppy dogs so that, yeah, they're right around 800. Switched and won is at 803, and stayed and lost is at 820. They're about the same. And also, stayed and won and switched and lost are about half of that. Now, if we scroll down to the bottom here, this is the probabilities that I've kept track of. If you switch, the chance you win is 0.66. Brian, that's really close to 2/3, isn't it? That's exceptionally close to 2/3. The chance you lose, therefore, is the other 1/3. Now, what you're seeing up there is you're seeing those represented in this column of the chart. This guy is twice as big as this. That means that's 2/3 of the total. Over here, the same thing's happening, but reversed. Look down here. If you stay, the chance you win is only 0.33, which means the chance that you lose is the other, well, 0.33 is 1/3. The chance you lose is 2/3. Now, please notice these are not exactly, well, they just switched over. I was going to say they're not exactly equal to 2/3 and 1/3, because the 2/3 and 1/3 are theoretical probabilities. These are actually based on the data of the experiment, and as you can see right now, over almost 3,000 trials. So hopefully you're seeing this is pretty convincing evidence that if you switch, you're going to win 2/3 of the time. So theoretically, in the video I explained to you why it makes sense. This, I think, is even more powerful because this shows you empirically why you should switch based on the data collection of the Monte Carlo and repeated trials. All right, my man, great question. I hope this makes sense. Hope it finds you well, and we'll talk to you soon. Be well. Happy New Year.